Thank you, everybody, for coming here, and thanks for inviting me to the conference. So, today I'm usually talking more about offensive security, but today I'm going to be talking a little bit about what can you do if you make your own chip in terms of offense and defense and research. So, the story starts sort of during the COVID period when we were doing some sponsored research. Because as riskier, we've done a lot of side channel analysis, fault injection. You might know of that sort of area that we're doing. And with a lot of customers, you figure out, okay, they have a problem or not. But if they have a problem, you're kind of too late. The chip's already there. You have a problem. So we were starting to think about, okay, can we do something pre-silicon, as we call it? So while the chip is being designed, can we simulate side channels or fault injection? So that was sort of the bigger topic of the research. And it was in collaboration with some actual chip designers and some universities. And we were trying to solve sort of this problem of side. This was specifically on side channel. And the cool thing is this was funded research, so we could actually go out and make our chip in like a 12 nanometer process. And then disaster struck. Due to some sort of boring administrative reasons, one of the partners got acquired, our funding got cut. So all of a sudden, we had no more chip maker friends to make a nice 12 nanometer chip. Also, we only had 6 weeks left, I think, till the end of the project. And this is around the time when eFabless, I don't know if you guys have heard about that, but they were around for maybe a few years. And they allowed you to make a chip for $10K. US dollars. So we're like, 6 weeks, $10K. Let's give it a shot. So essentially what eFabless does is you sort of make a chip design that goes into what they call Caravel. So Caravel is sort of a harness around it. You see in the... Now, can you guys see my mouse? Yeah. Okay. So this Caravel thing... So you get to define what happens in this white space. Here's a RISC-V core for sort of management and GPIO and UART and some basic interfacing. And then you can make a chip. The only thing is we're not chip designers. So this was a slight disadvantage we had. But a colleague and I had, we have some colleagues who actually knew how to program FPGAs and things like that. A colleague and I had just taken a course called Zero to ASIC, where you essentially start off at zero, and the goal is to make an ASIC. So we knew a little bit about RTL programming. And just to set a few terms for people who are not familiar with this, RTL is sort of the code that you write to functionally define what your part of your chip has to do. It can be a crypto block or a RISC-V core or whatnot. Then you do a process called synthesis. And that turns your design basically into a series of logic gates and flip-flops, like AND gates, OR gates, and flip-flops. Once you have the logic ready, then you have to sort of figure out where it goes physically on the chip. Right? All these things need to become transistors, and they need to become wires. And that's sort of what the placement and routing does. So if I talk about any of these things, that's sort of going from the logical design all the way to the physical. And what comes out is a so-called GDS file, which is essentially almost like a vector graphics file of literally where all the things are in the chip. So, okay, we, on a small scale, we had learned how to do this. So now it was time to do it for real. And the first question we asked ourselves was, okay, what do we actually want to do with this chip? So obviously side channel faults, that's sort of the thing that we enjoy. So we're like, okay, let's just take some open source cores. In this case, an open source AES, open source RISC-V core, 32-bit core, some open RAM, and then this multi-project tools, which is, I'll get to that in a second. And the idea is, okay, we have some AES cores, so we can do side channel on it, we can fault it, and we'll do the same on this Pico core. But the cool thing now is we have this complete GDS design file as well. So don't just have a black box chip that we, don't really know what's going on. We know literally where every transistor is in that thing and what it does. So, well, that was really cool. Normally when you make a chip, these kind of blocks, so this is actually the physical layout. You can tell I'm not a real chip designer because I made the physical layout in Inkscape. It turned out it's really well with coordinates and all that, so I placed it all by hand. But then you got to sort of tie them together. So normally this is done by some sort of bus infrastructure. We were a little bit more, let's say, reluctant to connect everything up to a bus because we had no idea if this was even going to work, right? If one of the cores is really messing things up on the bus, then maybe we can't talk to any of them. So we use this project called Multi-Project Tools, which basically allows you to cut off block, or actually by default, all the blocks are sort of cut off from that RISC-V management core, and you kind of turn them on individually one by one. So even if one is like complete garbage, just don't use that one, and then you're good. The downside is, of course, we cannot do things at the same time, but this is just a test chip, so that's all good. So that's sort of the layout of what we have. So let's go have a look at what we can do now that we have, we went through the process. So we submitted all this. We made the RTL, we submitted it, synthesized. And that's all, the cool thing is it's all open source tooling. So that whole flow goes, even chip designers non-chip designers like me are able to tape this out. So we got our chip back and okay, let's go play with it. So the first thing we were, looking at is fault injection. So we have this Pico RV32 core, which is a very small core that implements RV32 IMC, I believe. And we took one of our sort of basic test programs and compile it for that chip. And what it does is it sort of represents a very basic tests on a conditional branch. So we call it secure boot. It has nothing to do with secure boot except that at some point you make a decision whether you want to continue, executing the application or not. And normally you do that after signature verification. In this case, we're just reading a 1 or a 0 from a GPIO, and then based on that, we decide to boot the image or not. So since we have the RTL, we can also simulate this thing. So we actually take a Pico RV32 core. We actually took our netlist of it, simulated it, and we can start at any point in time, we can start flipping registers or outputs of logic gates. And that was sort of our proxy fault injection method. So we did that, and essentially because this is a small program, Pico RV32 is small as well, so we can actually try out, brute force all single bit faults on this. So essentially for every clock cycle, for every gate in the design, we inject a fault and we see what happens if we execute it till the end. Now, there's lots of times actually nothing happens. Sometimes the thing crashes, and every now and then it actually goes into this success branch. Oh yeah, I should say in our simulator, we always, I think success is always 0. So we read from this simulated GPIO, we always say 0. So it should always go into the failure branch. But we're simulating this, we're injecting faults, so we can detect, oh, wait a minute, it went into the success branch, and we mark that particular clock cycle and that particular gate as one that is sensitive to faults. Here you see a little bit of the statistics around that. I don't know if it's large enough to read or not, but there's about 408 different signals that you can glitch in order to get it into a successful branch. And some of them are more sensitive than others. I should say there are multiple clock cycles in which that signal, if you tickle it, it will actually put you in the success branch. The top 3, I don't know if you can read it, but these say Pico RV32 Reg Next PC. So these are actually fault injections directly on the program counter in the register bank in the Pico RV32. So it's essentially jumping by flipping a single bit in the program counter. And if you do that at the right point in time, of course, you jump into the happy flow or into the success branch. So we're like, okay, cool. We have some statistics about where this is sensitive. I should actually say I made a mistake. We did this simulation prior to making the chip. So this was the simulation part. Because what we want to do is we actually want to make a hardened copy of this CPU as well. So we took the Pico RB32 vanilla design, synthesized it, did the fault injection, and then for every gate that we found that, if we inject the fault there, it gives us an advantage as an attacker, we added what's called TMR, or triple modular redundancy, which basically means that instead of having just one gate or one flip-flop there, you make 3 out of it, and then you do a majority vote. So that means that if this signal originally was high, we should have 3 highs here, and then the output will also be high. But if one of these 3 gets flipped through a fault injection from high to low, the output of this whole signal will still be high. So majority voting meaning, you need 3 out of 3 or 2 out of 3 signals to still be correct, and then the output is still correct. So it adds a little bit of hardening to it. These are 2 input NAND gates, and this is 1 3 input NAND gate. So you're adding area, and you're adding more gates here, right? So your design gets a bit bigger. But the cool thing is we're, of course, doing this very targeted. We're only doing it, and maybe a little bit too targeted, because we're doing this very specifically for one particular program. We haven't tried other programs, so I wouldn't recommend this as a general strategy, but, we're just playing around. So we did that, and what you see here is part of that physical layout of the chip. Here in the center part, you see the vanilla Pico RB32. It had 13,320 gates. And on the right-hand side, you see the result of our hardening. So it actually only hardened 656 extra gates. Sort of on the input. Now you need to multiply that by about, I think, 7 or so to add all the majority stuff. And then in the end, you get 17,256 gates. So it got about 50% larger or something in terms of gate count. And it was cool because in simulation, we could now do the same experiment. And of course, simulation, we kind of know that then the number of faults is going to go to 0. It's kind of expected because we're only doing single bit faulting. Of course, if we would do a multi-bit faulting, if you do it in one particular area, then you might still override the majority voting and still get a fault. So it's not like this thing is completely insensitive to fault, but at least when we do this in practice, we should see the fault rate go down. So fast forward to when we got our actual chip back. We got very excited. So the way that this works is you have that management core in the top left here. I don't know why I blanked this out, but essentially there's what's called Open RAM. So it's a small SRAM. I don't actually remember how small it was, but it's really small, like 16 kilobit or something like that. So you can load a really small program in there from the management core, and then you can say, okay, we select Pico core, you go, and then nothing happened. And to this day, we still don't know why it's not working. So this was, a little bit of a reality check, unfortunately. This is actually why making a chip is hard, because how are we going to find... In simulation, this works, by the way. We can simulate that whole chip and it works fine. But why it's not working in hardware, yeah. Simulations aren't perfect, and somewhere in the cracks there's something's not working. So eventually, like, okay, let's move on. We have a bunch of AES cores that might also fail, but let's go test them. So for AES, we were more looking at the side channel stuff. So we're running crypto. Let's see if we can pull the keys out. I should say this is what's called a 150 nanometer process, which is, I looked it up, it's about like the Pentium 3, 4 era. It's like a really old chip process. And we therefore know that this thing, if there's no countermeasures, it's going to leak like a sieve. Like, this should really not be hard to break. And going in with that, and remember we had 6 weeks, we were working with our university partner. or thought, like, could we maybe make some variants of this AES score? We have a bunch of space to work with. And like, yeah, maybe we can add some like sort of inexpensive countermeasures that maybe sort of would work. Turned out they didn't. It was based on some balancing bits, meaning that if sort of one bit flip happens somewhere, then you kind of balance it out with another, but not quite like dual rail type technology where you really do a proper balancing. This was a sort of a poor man's balancing, and it didn't work, but it was fun to play with anyhow. We made 7 AES variants based on domain-oriented masking. So there's an open source project that I referred to in an earlier slide. We took that sort of as a basis. We created one share core, which is a fancy way of saying it's unprotected. We had a 2-share core, which had countermeasures on essentially, and then proper countermeasures, and then we had sort of our janky countermeasures. So we first started off putting this chip under an EM probe. So we're just running AES over and over again and looking at what the electromagnetic field does. And in order to sort of first quick scan, we saw traces like this, which actually looked fairly good. Maybe to the untrained eye, hard to see, but there's actually sort of the AES starts from here at 20 to about 200. You kind of see it sort of dipping down there a little bit. We can do more advanced techniques to sort of identify it, but sort of the first sniff test was okay. It's like, okay, hey, it looks like AES is happening. We were getting ciphertext back as well, so we actually know functionally these cores were working. So that was a small victory. But we wanted to sort of zoom in. We want to see like where does the leakage actually originate from within these cores. So the first thing is you scan over the chip. So you're going to, we knew this chip ran at 10 megahertz. It's not very fast either. 10 megahertz. And we're just going to look at the spectral intensity of the 10 megahertz signal. So we take signals everywhere. We do a Fourier transform and we look sort of at I think it was 9 to 12 megahertz. We look in that band, how much energy is there. And you can sort of plot that on an XY grid. So each dot here was one of those traces taken, and then we look in the 9 to 12 megahertz range. And you see some kind of nice looking areas happening, and red in this case means there's a lot of activity at the 10 megahertz. What you can also see, or actually what you cannot see, is any activity related to individual cores. So the sort of dark shaded area, that's where the die is within the larger package. I don't see like any specific core light up here, which usually means that you might be too far away, or you have a probe coil that's too large of a diameter to sort of make out those, the small resolution. And this was a relatively large. I believe this was, I think it was 0.5 millimeter diameter coil. So the problem with smaller coils is you also have to get closer to the die. And we were already touching the package. So I had to go to my good friend, John McMaster, who's really good at decapping chips. And the first step, you see the chip package in the middle here. If you look really closely, you see a red laser outline as well. That's sort of the area we're going to start milling down. So the first step is we just do a laser etch to get sort of closer to the die, but not all the way. And the second step is, chemical warfare. So you use fuming nitric acid to dissolve the rest of the package. And then you can actually see, if you look closely, kind of the shiny die areas there. So now we can actually get to the die itself physically. With that, we can get our sort of smaller diameter probes as well. So I believe this one is a 100 micron diameter coil, and we can get really close to the chip. Just to give you a zoomed in version there. For reference, I think this is about 3 millimeters and this is about 5 millimeters. So it's a lot larger on the screen. So, okay, good. We started scanning, and we didn't get AES anymore. So what now? We got AES before, right? So it's not a logic issue. So I don't know if you guys can see it. Well, I gave it away on the right-hand side. But if you look really closely, you see here one of the bond wires that's no longer nicely on its pad. So somewhere during the scanning or the handling, we just touched one of these bond wires and it snapped off. Luckily, we had a few backups. So we got this one away and we redid our scan. And what we specifically did is this AES core on the bottom right here, we call it core G. We ran AES on that core, and we're doing what's called a t-test. Now, if you're not into side channel, that's fine. Essentially, what we're isolating, it's a statistical test that will show us actual leakage from the key itself. So it's a really good indication of like, okay, something's going on here. What we did not see, well, we sort of see some leakage close to core G, but also in this core and also in the top right. So this was actually kind of interesting. Like we're not seeing it originate that strongly over a particular core. And we tried core A as well. I don't have that picture here. A is the top left. And the leakage was actually not substantially different than what you see here. So it looked like the leakage we were measuring in the EM field was still not coming from a particular core. So I'm like, okay, that's interesting. But what we can do now, what we couldn't do before, is we can sort of literally trace where the power is coming from. So we went into our layout tool, and again, we loaded this GDS file, which essentially has everything of the chip itself. And we started just at one flip-flop in core G. So this is sort of what it looks like, that one flip-flop. So this holds one bit of state. And we can start figuring out how this thing gets powered. So the first thing you do is you start enabling, so chip design or chip building, chips are made out a stack of layers, right? So at the bottom you have sort of the gates and the silicon, and you have different metal layers on top that connect all the things. So what I've enabled here is metal 1. That's sort of the first one that's sitting just above the silicon, and you see these sort of broader lines that are actually the ground and the power to this flip-flop. If I zoom out a little bit further, here's the flip-flop, and we follow ground in this case, or power, doesn't matter. You see that it gets connected to this sort of broader thing that's going up and down. If we zoom out even further, here you see those broader lines. They're sort of interleaving power and ground. They connect at the top of the chip to these yellow power lines, which then connect through the side and metal 5. And then if we go down a little bit, we actually see how metal 5 is connected to the pads. So we can actually sort of physically, I'm sure there's tools for this, but it's really cool just going in Clayout and doing this manually. You learn a lot about chip design. So yeah, you end up at actually the pads, which is where those bond wires, those golden wires you saw in the pictures before, they attach there, and that's where you get your power and your ground and all those things from. And if we look at the areas right here and right here, where we see leakage, that's exactly where there's some ground and power lines. A lot of these other wires / pads are IOs and a couple of other powers and grounds that didn't leak. So yeah, we could really trace it back to the bond wires. And that's actually where most of the leakage is apparently coming from. And it makes sense, right? These are relatively quite long. You have a lot of power going through them. With VCC and ground right next to each other, you might actually amplify the leakage because of the way that the electromagnetic fields interact together. And that was kind of an interesting observation because we don't always see this in sort of large SoCs that we test in our lab. But remember, this is really a simple test chip that's only doing one thing. So the power, while it's doing AES, is basically only related to AES. Whereas if we're doing this on a large SoC where EM may actually be beneficial over the die, it's because there's so many other things going on that actually cause sort of noise on the power line. But yeah, it was cool. We could finally sort of literally trace through the chip on how this leakage occurred. So moving to our original goal of sort of comparing power simulations with power analysis, there's a publication. I put a link here, but in a nutshell, what we're doing in that particular paper is we're taking a chip design, and it allows us to identify within the chip when and where leakage occurs for side channels. So it literally gives you a pointer as a designer, like here and here and here. At this point in time, you have leakage. Go fix it. That's the kind of output we want during design time. So we took that software we have, and we identified the top 50 leaky signals in that design. And then what you see here is essentially these, well, not all 50, but you see the top, I can't count that quick, 20, 30 or so. And over time, you see that these signals go between 0 and 1, as signals do as you're operating on some data. And what we did is we are going to use the toggles as a very crude proxy for power consumption, because it turns out toggling circuits, that's what sort of dynamic power usage of a chip comes from. And the more toggles, the more power. So let's just add the number of toggles up over time and pretend that that's our power consumption. And it turns out that actually quite well relates to our measurements. So at the top, you see those toggle counts. So over time, you see them go up. This is related to the AES activity. Interestingly, you also see that before the AES starts, there is, those signals are actually not doing anything. They're not part of the leakage. So they were, the signals that were not part of the leakage weren't being simulated. So there's 0 toggles there. Makes sense. Then at some point, you see these toggles happening. And if you're good at counting, you can count to 10. You see the 10 rounds of AES here being represented. And when we take an EM measurement, we have to do a little bit of signal processing. So there's some rectification and some low pass. But you can kind of see the same pattern there. And these were the kind of, there's a lot more to this, but I wanted to sort of visually show you that, these things, they are related. And you can do much more precise power modeling, but at least at this level, it already allows us to identify when and where leakage is happening. So there was one, that was all the science stuff. Now the cool stuff comes. There was one mystery block that I had blanked out before. So we ran out of ideas for AES blocks. Actually, I think we had an 8th AES block, and for some reason that sort of failed in one of the last stages, and we were about 5-6 days away from the tape out deadline. So okay, scratch the block. And at that point, I got COVID. I'm fine, as you can tell. But I got COVID then, and I decided to isolate within my house for my family. So I had a lot of time on my hands. I was asymptomatic. I was like, okay, my desk is in my bedroom. I'm all here alone. What am I going to do? So I decided to make, there's a tradition if you're looking at chips. There's a tradition of doing chip art, like little doodles in chips. Now, I'm a terrible artist. So I'm not good at drawing. I think for the traditional chip art, you usually use this magic tool. I'm not good at that. So I was like, let's just make a PNG to GDS converter. How hard can it be? So this is eventually what I came up with. Obviously, we had to put our company logo there, and I put a couple of funny things in there. But actually, it turned out to be a little bit harder than I expected, because on the initial run, I was like, okay, great. I could see this in Clayout, and you start going through the chip process. And at some point, there's a stage called DRC, which is design rule checking, which is essentially where the tools will tell you whether this is even manufacturable or not. You cannot sort of arbitrarily send things to a fab and then hope that they will send it back to you in a working order. So the first one was actually relatively simple. So it was like, this IP block is not connected. Like it is not connected to power or ground. It's like, okay, well, that's easy. I essentially I think I made this into a huge capacitor, because on one end I just drew a large VCC line, on the other side a large ground line, and then all the tools were almost happy. It was that error was then gone. But you run into some other issues, because zooming in a little bit further, what the fabs also don't like is if you have two pickles that are sort of diagonally from each other. Now, I could have made taken a PNG that didn't have that, but I wanted to have Space Invaders at 21.8 micrometer. For reference, a human hair would cover this completely, this thing. So it's really tiny. So I had to solve this. So I was thinking, well, I actually have a couple of metal layers I can play with. So maybe if I just put some part of the images on one metal and then others on the other metal, maybe it will be okay. So actually, it turns out that is true. So you have to do a little bit of computer science 101. So you clustered things, and then you do some graph coloring on, which metal do things go onto. And then you can make these kind of beautiful pictures. So, I don't know if there's an official category in the Guinness Book of Records for smallest Space Invaders, but I think I'm a pretty good candidate here. So with that, I was thinking what's actually the takeaway from this talk. So I'm a very curiosity-driven person. It's always sort of been my thing, and I always want to look deeper in how does this actually work. So I've reached now a level where I can actually look inside my own chip design and figure out how things are going, both on the dynamic side, so we can simulate all these things, but also the static side on how everything's laid out. So for me, this was very satisfying in the sense that you just have so much more visibility, right? I've been doing side channel and fault for over a decade, and it's always sort of black box. We know we can break it, but we don't really know how. We get a lot more insight this way. What I also find really cool is if I can do it, you can do it too. I had a company that paid $10K, so that makes some things easier. But there's something called tiny tape out, where for $100 you essentially get a small piece of a chip, and you can put arbitrary things in there as well that you're interested in. So go have a look at this tiny tape out. This chip technology, again, it's really large, so it leaks. So you also don't need the expensive lab tools that I have access to. You can just do with anything that's more accessible to hobbyists, like Chip Whisperer type tools. And this whole flow is also open source tools. I'm also working on trying to open source the work that we did, because it was externally funded with a few parties. There's some hoops I have to jump through, which I am jumping through right now. I'll announce it once I get it up on GitHub. But for me, I think one of the more fundamental takeaways here is that there's really this interesting relation between breaking and making things. So anybody who's broken something knows that if you have made something similar, it kind of really helps you to analyze it and find the flaws. But also the other way around, right? If you want to make something, but you know how it breaks, that also really helps you. And I think that has gotten now down to the chip level, where you and I can do this. For me, that was a very enjoyable process. Finally got to make a chip. I still don't go as far as calling myself a chip designer, because I'm very clearly not. But you can get something out there that works. So that was pretty cool. Anyway, thanks for your attention. Take any questions.
Thank you, Jasper. Yes, we have some time for questions before we go for...
One here.
Yes, we've got a question there. Any other question on this side? Yes.
Hello, thank you for the presentation. You said that
there.
Yeah. The processor is pretty old, you said, but you still had to decap the chip. Is it usually the case that you have to decap the chip in EM side channels or not?
Yeah, it's a good question. So for key extraction, we absolutely did not have to decap this. Like, it was very leaky you could probably hand make a coil and get a cheap oscilloscope and get the keys out very easily. The reason we decapped is because we wanted to sort of zoom in and see, is the leakage coming from this IP block or from that one, and where within the block, which eventually turned out to be bond wires, but at that point we didn't know that yet. But that's why we decapped.
I see. Another question is for fault injection. You talked that the solution is using triple redundancy, but for side channel, what would you say is a solution for the counting?
So the solution is really hard. And that has to do with, there are theoretical really good countermeasures out there, but they come with a cost. They come with an area cost, a performance cost. And, we have that 2-share implementation, which theoretically resists any first order attacks. So anybody can go out and use that. The problem is in reality, chip designers have limited area and limited resources to work with. So that's where it sort of becomes a trade-off of, okay, I can use the perfect countermeasure, but maybe it doesn't fit. Okay, maybe I have to tone it down a little bit. And that's when leakage occurs. So yeah, there's definitely a lot of interesting literature on countermeasures and good ones, but in practice, it's a trade-off question.
I see. Thank you.
Yep.
Great. We have a question on this side.
Yep.
So first of all, thank you for the great talk. You were talking about the majority voting for the with the NAND gates. So did you do any testing on the AES cores with that? So if it actually made a difference for fault injection, and what would actually prevent you from just hitting the output of the NAND gates? So if the EM pulse would just couple into the output, it would basically be useless, right? Or not?
Yep. Good question. So I think I hear two questions. So the first one on the AES core, the answer is no, we didn't use TMR. The reason there is that a very large part of the AES core is actually the data path and the S boxes. And if you add TMR to that, it actually gets many times bigger. So this is actually not why we didn't do it, but that's why in practice you use TMR not on sort of these crypto engines. And there's different ways of checking for faults. Like actually what you often see is things like run the crypto twice and check whether the output is the same, or do an encrypt and a decrypt and see if you get the plain text back. So those are countermeasures that are cheaper in terms of area to do. And then the second question, of course, I'm blanking on. What was the second part of your question?
What would actually prevent you from hitting the output of the NAND?
Yeah. So nothing. Nothing is preventing us there. But the nice thing is this is again an input to some other gate, right? So in the end, this is one large network, and we cover all the faults here. So it turns out that if the input, so what I left, so this is TMR, but it doesn't show the actual gate that I'm TMRing. So I'm also doing, if this is an OR gate, I also have 3 OR gates here. So what it's saying, if I have one output there, is that one output actually didn't lead to the fault that I cared about. And if the input was important, then I made it triple redundant anyway. So that's sort of how that works.
Hi, thank you for the very interesting talk. I was wondering, I'm not a chip designer, so maybe this is a silly question, but I was always wondering, as a simple mitigation, and suppose you have a little bit of wiggle room in terms of area, would it help to add some, low-hanging fruit, like adding a bunch of capacitors in your design on the VCC and ground lines, and putting a huge ground plane on the top and the bottom, with some insulator in between that is, glued to the traces? So if you remove it, that you destroy the traces. Would measures like that help?
Yeah, they all help a little bit. So these are sort of common things we see on, especially in like the sort of area of secure microcontrollers, smart cards. On a modern one nowadays, if you're measuring on VCC, it's going to be really hard to see any side channels. Even EM might still be pretty hard. And that has to do because this is one of the countermeasures. They usually have a whole stack of them. Doesn't mean they're unbreakable, because yes, you have a little bit of wiggle room, but not infinitely much wiggle room. So it usually becomes a question of how hard is it to break it. And when you look at, for instance, certification schemes, they just set an upper limit on that. So if you can't break it within, time X, resources X, money X, then we call it good enough.
So how would you quantify those measures in terms of cost and area?
In terms of cost and area, that's not my expertise. But in this, what I can say is in the secure microspace, one of the main goals is to be secure. So there's a lot more sort of wiggle room in terms of adding countermeasures. Stuff we've also seen in other chips is things like dual lockstep. So if you have a CPU, you can actually add a whole copy of that CPU and then sort of check whether the input and output signals are the same. So that's one redundancy measure against faults that you can use. That probably doesn't help much with side channel. Probably doubles the signal, but these measures are usually more for critical systems as well, like in your car ECUs and stuff. You don't want, if there's one CPU that fails, you kind of want to detect that and recover from it. So, but they also double as sort of a fault injection countermeasure. Again, not a perfect one, but yeah, you get some way.
Great, thank you.
Yep.
Thank you, Jasper.
Yeah.
Jasper.
Jasper.
Let's give another round of warm applause to Jasper.